Hey everyone, welcome to the live class. I hope you can see my screen and hear my voice, right? So let's wait one more minute and then we'll start. All right. So in the last class, I discussed this chapter, atomic structure. So I talked about the atomic number, mass number, isotopes, the electronic structure or electronic configuration, all that stuff. Basically, I finished atomic structure in the last class of chemistry. Today, I'm going to cover the composition of matter. In fact, this is the first chapter and this is the second chapter for the IMAT syllabus, not the A level. So in this class, I'll do composition of matter. And to start this chapter, let's talk about states of matter first. This is a very simple concept. Basically, there are three states of matter: solid, liquid, and gas. And solids have high density because in a small volume, there is a lot of molecules of solid present. So in a small volume, since there is a lot of solid atoms present, solids have high density, liquids have medium density, and gases, because in a fixed volume, gases will have the lowest number of molecules present. So gases have a low density. Now, solids can't move a lot, so they are regularly patterned. Liquids are randomly arranged, so they can move a little bit, but gases are randomly arranged and they have big distance between each molecule. Now, solids, because they are fixed, they only vibrate around a fixed position. Liquids, they move around each other because they have a little space in between them. And gases, since they have large distance between them, they move quickly in all directions. Now, solids have low energy and gases have the highest energy. Why is that? Because gases move the most. They have the most kinetic energy between them. They have high speed, so they have the highest energy. And solids can't move a lot. They have low kinetic energy, so low energy. Now, I think this is pretty much what state of matter is. So this is what you need to know for state of matter. Moving on to heterogeneous and homogeneous systems. This is a very important concept. So let's first discuss homogeneous mixture and heterogeneous mixture. You need to know the differences. So a homogeneous mixture is that mixture in which the components mix with each other and its composition is uniform throughout the solution. Whereas heterogeneous mixture is a mixture that in which the composition is not uniformly throughout the different components that are observed. So heterogeneous, they do not have uniform composition. So no uniform composition, whereas homogeneous have a uniform composition. Now, homogeneous mixtures cannot be seen through the naked eye. You can't see through these homogeneous mixtures through the naked eye. Whereas, wait. So, whereas heterogeneous mixtures can be seen through the naked eye. What are the examples of homogeneous mixtures? Well, salt solution or sugar solution. So when you take water and you mix sugar in it, can you see the sugar molecules when it's completely mixed? You can't, because the sugar is completely dissolved in the water. Whereas heterogeneous mixture is mixture of salt and sugar, or grains and pulses along with some dirt particles. So let's say you have sand molecules and you throw in some sugar in them. You can clearly see the white sugar from the brown sand particles. So this is an example of heterogeneous mixture. So moving on, in homogeneous mixtures, the component size are at atomic level or they are very small. Whereas in heterogeneous mixtures, the size of particles are large. That is the reason you can see the particles with your naked eye. homogeneous mixtures cannot be separated easily. Once you mix sugar in water, you can't unmix the sugar because it's completely dissolved now. Whereas in heterogeneous mixtures, you can clearly separate the two mixtures. So if I put sand in sugar, I can remove the sand particles and sugar through filtering. The constituent particle in a homogeneous mixture possesses the same physical properties, whereas the constituent particle in heterogeneous mixtures possesses different physical properties. And that is pretty much homogeneous and heterogeneous mixtures. Now, this is not that important compared to what I'm going to teach right now. This concept, catalyst, is very important because there are two types of catalyst that you need to know: homogeneous catalyst and heterogeneous catalyst. So, in a homogeneous catalyst is the catalyst that has the same physical state as the reactants. So, let's say the reactants were gas and you make some product, right? Now, what homogeneous catalyst says is that the catalyst that is used will also be a gas molecule. So, for example, SO2 reacting with oxygen produces SO3. So sulfur dioxide with oxygen produces sulfur trioxide. Now the catalyst used here is nitrogen dioxide, and nitrogen dioxide is a gas. And the reactants that were used were also gases. So NO2 here is acting as a homogeneous catalyst. Whereas heterogeneous catalysts are catalysts that is in a different physical state compared to the reactants. So if let's say that now instead of my reactants are, let's say that my reactants are still gas, but the product now, but the catalyst now, sorry, would be the catalyst would be a solid instead. Solid, liquid doesn't really matter. What are the example of this? Well, the the most famous one is the reaction with nitrogen and hydrogen. So nitrogen and hydrogen would react to make ammonia. And similarly, C3H4 will react with hydrogen to make C2H6. Now, in this reaction, both of these reactants are gases, but the catalyst that I use right here is nickel, and nickel is a solid. So since nickel is a solid, this is a heterogeneous catalyst. And the mode of action of both of these catalysts are different. So I'll explain you before before I get to this part. Now, what does a catalyst do? A catalyst simply reduces the activation energy of a reaction. So let me zoom in right here. So let's say that this right here is an energy diagram. So without a catalyst, right? When I don't use a catalyst, this would be the energy cycle of my reaction. But when I use a catalyst, this, so I'll explain this again. So let's say this is the energy diagram. Now, there are two energy cycles right here, this cycle and this cycle. This right here, this cycle where the energy required is huge, is where I don't use a catalyst. But when I use a catalyst, right, when I use a catalyst, this would be my energy diagram. You can see that the energy required for uh, the activation energy when I use a catalyst is much less compared to that when I use a catalyst, when I don't use a catalyst. So catalyst simply reduces activation energy. Now, you don't need to know the mode of reaction of homogeneous catalyst, but for the exam, you do need to know the mode of action for heterogeneous catalyst. So how does heterogeneous catalyst work? Well, there are three different steps. So first step is that, let's say that this is the catalyst, which is a solid, and gas molecules, right? Gases will diffuse to the surface of the catalyst. So gas molecules will arrive at the surface of the catalyst, and then something called adsorb happens. So what is adsorb? So the the gases would arrive to the surface of the catalyst, and they will make bonds with the surface. This is known as adsorption. So the gases reach the surface and they make new bonds. This is called adsorption. After adsorption, the same bonds will break and form new bonds, but the weaker bonds will break and form new bonds. So the weaker bonds, right, between the gas molecules would simply break and form new bonds. And when this happens, the next step after forming these new bonds is called desorption. Desorption is when the gas molecules form new bonds and they simply break off. So there are three steps for this reaction. They diffuse to the surface. This is step one. Step two is adsorption happens, where the gas molecules form new bonds. This is called step number two, or this is also known as adsorption. And step three is desorption, where the gas molecules would break off from the solid catalyst. So when these gas molecules get away from the catalyst, this is called step number three, or simply desorption, right? And this is pretty much heterogeneous catalyst and homogeneous catalyst. So when I go back to the, let me go back to this syllabus. Yeah. So I'm done with state of matter, heterogeneous and homogeneous systems. Now let's go on to compounds and elements. Now, what is an element? An element is a substance made of atoms that contain the same number of protons and cannot be split into anything simpler. So element is basically the building block, right? It can't be broken down any further. But compounds, right? Compounds are substances that are made up of two or more elements which are chemically combined. Now, this chemically combined is called a bond. And there are three different bonds that I'll talk about in the next class. But for now, a compound is a substance that is made up of two or more elements which are chemically combined. And there is an unlimited number of compounds. And compounds cannot be separated into their elements by physical means. Example of compounds are calcium carbonate, carbon dioxide, water is a compound, H2O, right? So there are three elements in a compound of H2O. So what is a mixture? A mixture is a combination of two or more substances, elements, or compounds that are not chemically combined. So in a mixture, you mix two substances together that are not chemically combined. So sugar and water, when you mix that, you don't form a chemical bond. You are simply mixing them without forming a chemical bond. So mixtures can be separated by physical methods, but compounds cannot be separated by physical methods. What do I mean by physical method? Well, when I mix water with sand, I can separate the sand using a filter. This is called physical methods. Example, sand and water, oil and water, sulfur powder, and iron filling. So oil and water can also be separated you can easily separate oil and water because they have different densities, right? So let's go on to the summary now. Elements, you need to know the definition. Element, the simplest type of substance made up of only one type of atom. Compound is a substance that contains two or more elements chemically joined together in fixed positions, in a fixed proportion. And a mixture is different substance in the same space, but not chemically combined. Is this AS level? No, this is IMAT. So the full list of elements that are diatomic, you need to know the elements that are diatomic. These are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Basically, when when an element exists in a natural state where they form bond between them, this is known as a diatomic molecule. So you need to know all of these diatomic elements. You have to memorize them, and they won't give you the periodic table. So it's better if you literally memorize them. Now I will move on to the final and the most important topic for this chapter, which is the ideal gas. And in every paper, you will find questions related to ideal gas. And ideal gas not only comes in chemistry, but it is also present in physics. So what is an ideal gas? Ideal gas is a gas that doesn't obey the rules of a normal gas. So ideal gas has some assumptions. There is no ideal gas in real life. We have only assumed that an ideal gas is present. So the first thing that you need to know for ideal gas, diatomic elements ends with the term gen and ein. No, it doesn't end with gen or ein, but it's only the name. It's the natural name of these elements. There is no rule of naming them. Now, going back to ideal gases, the first rule is that ideal gases are composed of constant and random moving particles. This is rule number one that you need to memorize. Rule number two is that molecules which ideal gases are composed of act as rigid spheres. So an ideal gas molecule act as a rigid sphere. That's the second rule that you need to know. The third is that all collisions between the molecules of an ideal gas are perfectly elastic, and no kinetic energy is lost during the collision. What do I mean by this? Simply said, let's say there is two ideal gas molecules. When they collide, right? When they collide, the collision is perfectly elastic. So the collision is elastic, and when a collision is elastic, there is no kinetic energy that is lost during the collision. But let's say that instead of ideal gas, I had two cars and they had a collision, right? So when two cars collide with each other, they will stop, right? So they will lose kinetic energy. Kinetic energy will be lost during a collision between two cars. Kinetic energy is lost when there is a reduction in speed or velocity, because kinetic energy, everyone knows, is half times mv squared. So when this velocity decreases, you will lose kinetic energy. But in ideal gas, the collision is elastic. You don't lose any velocity, therefore no kinetic energy is lost. It was in an information in IB Pearson's book. Okay, so the fourth rule is that pressure arises due to the collision. So when an ideal gas molecule collides, the pressure of the container would increase, because they will collide and move back and hit the walls of the container. This will cause an increase in pressure. So pressure arises due to the collisions. And this rule is also very important, that intermolecular forces between the gas molecules are completely negligible. What do I mean by this? Well, ideal gas molecules have no intermolecular forces between them. So there is no force of attraction between these two molecules, because molecules essentially have protons and electrons, right? And let's say that this proton can attract this electron in a normal gas, but in an ideal gas, this is not the case. So we assume that there is no intermolecular forces between gas molecules. And finally, the volume occupied by the molecules is entirely negligible. What do I mean by this? Let's say I have a container and I have ideal gas molecules in that container. And what this assumption states is that the volume of these molecules are so small that is that it's completely negligible compared to the volume of the container, right? So now this formula is, you will find this in physics as well. So an ideal gas equation shows the relationship between pressure, volume, temperature, number of molecules of a gas. And this is called PV equals nRT, where P is pressure, which you'll use in pascals. V is the volume in meter cube. Sir, can you summarize the earlier topics at the end of the lecture? Yeah, I'll do that if I get time. Volume is measured in meter cube. N is the number of molecules of a gas. Now, this N, right, has a formula called mass over MR. You might have seen this in your high school. So instead of giving N, right, they can also give you the mass and the MR of the molecule. And they'll tell you, hey, I've given you the mass and the MR, find me the number of moles, and finally find me the pressure or volume using this formula. So R, right, R is a constant, and this has a value of 8.31. So whenever you see R, you can replace it with 8.31. It won't change. The value is a constant. And finally, temperature. This T right here is called temperature. And you measure temperature in Kelvin. Remember, Kelvin and not Celsius. So whenever you find a temperature, you will measure it in Kelvin. And let's say that they give you the temperature, they give you 32 degrees Celsius, and they also give you the pressure. Let's say pressure is 1 Pascal, volume is 1 meter cube, and they tell you, find me the number of molecules. So how will you find this? I'll give you 1 minute to do this question. They've given me the temperature, the pressure, the volume, and they tell me, find the number of molecules. Okay, so I'll use PV equals nRT, right? Pressure is 1 Pascal, and the unit is Pascal. I don't have to change the unit. So 1 times 1, because the volume is in meter cube. If it was in centimeter cube, I will have to change it. But right now it's not, so there is no need to change into meter cube. 1 times 1 equals to the number of moles into R is 8.31. And this, you will multiply 8.31 times the temperature. Now the temperature is 32 degrees, but I've told you earlier, the unit is Kelvin, and they'll always give you the temperature in Celsius, and you have to convert it into Kelvin. So how do you do that? Well, Celsius to Kelvin, right, is any temperature in Celsius. If you add 273 to it, this will become Kelvin. So 32 plus 273, I think it's 305, right? Let me use my calculator. Yeah, it's 305. So the temperature in Kelvin is 305 Kelvin. 32 Celsius is 305 Kelvin. Now, using all of this, I can find the number of moles. What is the number of moles? Well, 1 equals to 1 times 1 is 1, right? So 1 equals to 8.31 times 305 times the number of moles. And I'll multiply these two, move this to the left, and I'll get the number of moles. You have to do this without using a calculator. Remember this. So learn how to multiply numbers without using a calculator. Now, I'll do this using a calculator for now. So the number of moles I get is 3.9 times 10 raised to power negative 4. And Let's say that they give you the number of moles and you find the number of moles, and they tell you, I've given you the MR of a molecule. Let's say it's 89. And using this and the MR, find me the mass of the molecule. So how will you do this? I know number of moles is mass over MR, right? I have the MR, I have the number of moles. I can use this to find the mass. So this is the type of questions they can ask you in the exam. The ideal gas exception. Yeah. So this is a question from I think it's 2018 IMAT. I don't remember the question number, but I'll give you guys 3 minutes to solve this. This is a difficult question. So take your time, solve this. If you can't solve it, I'll solve it myself. Uh, okay, so someone said 2 and 3 in the chat. Someone said B is the answer, but let's see now. So a sealed container contains 1 mole of gas, hydrogen gas. It's D. Someone is saying E and D. So let's see now. So a sealed container, so there is a container that has hydrogen gas, which behaves as an ideal gas, right? So this 1 mole of hydrogen is the N in the equation. Now, when they say it behaves as an ideal gas, we will use a formula called PV equals nRT. This is called the ideal gas formula, and you'll use it whenever you see ideal gas mentioned in a question. So I know I'll use this formula. Now, which of the following changes increases the total kinetic energy of the hydrogen gas molecules inside the container? So they're saying, what will change the kinetic energy of the hydrogen gas in the container? Now, changing the amount of hydrogen from 1 mole to 1.2 mole while keeping the pressure and volume constant. Now, they said volume and pressure is constant, but I changed the number of molecules. So in this equation, right, what links kinetic energy? So kinetic energy, right? How is kinetic energy linked to this formula? Does kinetic energy change with pressure, volume, number of moles, or the temperature? It changes with the temperature. Kinetic energy, right, is directly proportional to the temperature. So when I have a container with molecules and I increase the temperature, let's say I put fire below this container, I increase the temperature, the kinetic energy of the molecules would increase. Why would it increase? Because the volume, the velocity, sorry, the speed or the velocity of these molecules would increase. They would move much faster, they would collide more. Basically, the speed would increase. And I know kinetic energy is half into mv square. V is velocity, m is mass. if I increase kinetic energy, my velocity increase. If I increase my velocity, my kinetic energy increases. So the point is, kinetic energy is directly proportional to temperature. So what do I want in this question? They're saying that which of the following changes increase the total kinetic energy? So I want to increase my kinetic energy. For that, I would want to increase the temperature in this equation, right? Because if I increase the temperature, my kinetic energy increases. So in PV equals nRT, what would increase the temperature? So changing the amount of hydrogen, meaning you change the number of moles, but you keep the pressure and volume constant. So these two are constant. R is also a constant, and you are increasing the number of moles. When you increase the number of moles, what will happen to the temperature? The temperature would decrease, right? Why? Because this side is a constant. You want to keep this constant. So if I increase the number of moles, I would have to decrease my temperature so that this pressure and volume remains a constant. So the temperature in one is decreasing. So if the temperature is decreasing, kinetic energy is also decreasing. But I don't want that. I want my kinetic energy to increase. So one is wrong because in one, kinetic energy is decreasing and not increasing. So in two, right? In two, they are saying that I change the pressure from 1 ATP to 1.2 ATP, and I keep the volume and number of moles constant. So I increase my pressure, I keep my volume constant, the number of moles also constant, and R is also constant. So all of these are constants. So when I increase my pressure, what would happen to my temperature? My temperature would also increase, right? So in number two, my temperature is increasing, so my kinetic energy would increase. Therefore, number two is right. And finally, the third one, right? They are saying that I change the volume from 1 liter to 1.2, but I keep my pressure and number of moles constant. So I increase the left side, right? I increase the volume. I keep my pressure, number of moles constant. So if my left side increases, my right side would also have to increase, right? But since these two are constants, my temperature would therefore increase because my left side is increasing. So therefore, temperature is increasing, kinetic energy would also increase. Therefore, 3 and 2 have increasing kinetic energies. So 2 and 3 is right, therefore B is the right answer. Is this clear? If you have any questions, you can ask now. Yes. Someone said, can you summarize the earlier topic at the end of the lecture? Yeah. So in the last class, right, I talked about, this chapter, atomic structure. So elementary particles are the electrons, the protons, and the neutrons. And protons are positive, electrons are negative, neutrons are neutral. So when I have two charged plates, meaning positive and negatively charged plates, I pass a proton through this plate. Then the proton will move to the negative plate because protons are positively charged. It will be attracted by the negative charge. Similarly, electrons, right? It's negatively charged. It would be attracted by this positive plate, and so they move to the positive plate. And finally, neutrons, right? They would go straight through because neutrons are neutral. They won't be attracted by any of the plates. Now, mass number is the number of neutrons plus the number of protons in a molecule. And similarly, if you want to find the neutron number, right? If you want to find the number of neutrons in a molecule, you would simply subtract mass number by the proton number. And also the atomic number, right? Atomic number is also known as the proton number. So isotopes are elements that have the same number of protons. So it has the same number of protons. The proton number is the same, but the neutron number changes. Isotopes will have the same number of protons, but different number of neutrons. And if the neutron number changes, I will have a change in mass number, because mass number is neutrons plus protons. And if the neutron changes, my proton number will change as well. And what else? Electronic structure of atoms and elements. This is a big topic. I don't think I can finish this in 3 minutes. If you want, I can send you my notes for this topic, but this is a big topic. It can't be finished in 3 minutes. I only have 3 minutes left for the class. So if you want my notes, you can message me on Discord. I'll send you the notes. Other than that, I think we are done for today. Okay, thank you, everyone. I hope you have a great day. See you tomorrow. Bye.